Another day, another story. The story of semiconductors is a fascinating journey that spans the realms of physics, engineering, and technology. Here's a comprehensive overview. Welcome to Turbo Eminent Channel. Early discoveries. The groundwork for semiconductors was laid in the late 19th and early 20th centuries with the discovery of the electron by J.J. Thomson and the development of quantum theory by physicists like Max Planck and Albert Einstein. These foundational theories helped scientists understand the behavior of electrons and materials. Semiconductor physics. In the 1930s, scientists like Walter Shockley and Karl Horowitz began exploring the electrical properties of semiconductors. Semiconductors are materials that have electrical conductivity between that of a conductor and an insulator. Silicon, germanium, and other materials were identified as promising semiconductors. Invention of the transistor. The breakthrough moment came in 1947 when John Bardeen, Walter Brattain, and William Shockley at Bell Labs invented the transistor. The transistor was the first solid-state device capable of amplifying electrical signals and switching them on and off. This invention revolutionized electronics by replacing bulky and unreliable vacuum tubes. Integrated circuits. Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor independently invented the integrated circuit in the late 1950s. This innovation involved placing multiple transistors, resistors, and capacitors on a single semiconductor substrate, leading to the miniaturization of electronic components. Silicon dominance. Silicon emerged as the dominant material for semiconductor manufacturing due to its abundance and favorable properties. The development of the planar process by Gene Hoheny and the creation of the first microprocessor by Intel in the early 1970s marked significant milestones. Moore's Law. Coined by Gordon Moore, the co-founder of Intel, Moore's Law predicted that the number of transistors on a microchip would double approximately every 2 years, leading to an exponential increase in computing power. This prediction held true for several decades, driving the rapid advancement of technology. Semiconductor industry growth. The semiconductor industry expanded globally, with companies like Intel, AMD, Samsung, TSMC, and others playing key roles in the development of increasingly powerful and compact electronic devices. The demand for semiconductors soared with the rise of personal computers, smartphones, and other digital technologies. Specialty semiconductors. Beyond microprocessors, specialized semiconductor devices emerged, including memory chips, sensors, and application-specific integrated circuits, ASICs. These components became integral to various industries, such as telecommunications, automotive, healthcare, and consumer electronics. Challenges and innovations. The semiconductor industry faced challenges such as shrinking transistor sizes, heat dissipation, and manufacturing complexities. Innovations like FinFET transistors and 3D packaging techniques addressed some of these challenges, allowing the continued progress of semiconductor technology. Future directions. The future of semiconductors involves exploring new materials, such as gallium nitride and silicon carbide, and developing novel architectures, such as quantum computing. The industry continues to evolve, driven by the demand for more powerful, energy-efficient, and specialized electronic devices. The story of semiconductors is one of continuous innovation and has played a pivotal role in shaping the modern world. From the invention of the transistor to the development of advanced microprocessors, semiconductors have become the backbone of the digital age. Semiconductor. Any of a class of crystalline solids intermediate in electrical conductivity between a conductor and an insulator. Semiconductors are employed in the manufacture of various kinds of electronic devices, including diodes, transistors, and integrated circuits. Such devices have found wide application because of their compactness, reliability, power efficiency, and low cost. As discrete components, they have found use in power devices, optical sensors, and light emitters, including solid-state lasers. They have a wide range of current and voltage handling capabilities and, more important, lend themselves to integration into complex but readily manufacturable microelectronic circuits. Bipolar junction transistor, BJT, After the invention of the point-contact transistor by Bardeen, Brattain, and Shockley, researchers like William Shockley and John S. Kilby further developed the bipolar junction transistor, BJT. BJTs became essential components in electronic circuits, amplifying and switching electrical signals. They were widely used in early computers and communication devices. Metal oxide semiconductor, MOS, transistor. In the 1960s, advancements in semiconductor technology led to the development of the metal oxide semiconductor, MOS, transistor. This type of transistor had advantages in terms of size, power consumption, and manufacturing. It paved the way for the creation of complementary metal oxide semiconductor, CMOS, technology, which is now the foundation for most digital integrated circuits. Memory advances. The evolution of semiconductor memory played a crucial role in the development of computers and electronic devices. Dynamic random access memory, DRAM, and later flash memory technologies allowed for the storage and retrieval of digital information, essential for the functioning of computers and portable electronic devices. VLSI and ULSI, very large-scale integration, VLSI, and ultra-large-scale integration, ULSI, refer to the integration of a large number of transistors on a single chip. The move towards VLSI and ULSI marked a shift in the semiconductor industry, enabling the creation of more complex and powerful microprocessors, memory chips, and specialized integrated circuits. Nanotechnology and nanoscale transistors. As semiconductor technology advanced, researchers began working at the nanoscale to push the limits of miniaturization. The development of nanoscale transistors, such as FinFETs, thin-field effect transistors, allowed for greater control over the flow of electrons, contributing to increased efficiency and performance in electronic devices. Quantum dots and quantum computing. Exploring the principles of quantum mechanics, scientists have been investigating the use of quantum dots for applications in electronics. Quantum dots are semiconductor nanoparticles with unique electronic properties. Additionally, the field of quantum computing aims to use the principles of quantum mechanics to perform computations at speeds unattainable by classical computers. Globalization and fabs. Semiconductor manufacturing has become a global industry with fabrication facilities, fabs, established worldwide. Companies like TSMC, Taiwan Semiconductor Manufacturing Company, and Samsung have played pivotal roles in advancing semiconductor manufacturing technology. The complexity of modern fabs and the enormous investment required underline the global nature and competitiveness of the semiconductor industry. Challenges and innovations in materials. Over the years, researchers have explored alternative materials to traditional silicon, such as gallium nitride GaN and silicon carbide, SiC. These materials offer unique properties that are advantageous for specific applications, such as power electronics and high-frequency devices. Impact on society. The impact of semiconductors on society is immeasurable. They have transformed communication, healthcare, transportation, entertainment, and nearly every aspect of daily life. The ubiquity of electronic devices, from smartphones to smart appliances, is a testament to the profound influence of semiconductor technology. System-on-chip (SoC) integration. The evolution of semiconductor technology led to the development of system-on-chip (SoC) designs, where an entire system, including microprocessor cores, memory, interfaces, and other components, is integrated onto a single chip. This integration has been instrumental in the design of compact and power-efficient devices, such as smartphones, IoT devices, and wearables. Moore's law challenges. While Moore's law held true for several decades, there have been challenges in recent years. The miniaturization of transistors faces physical limitations, such as quantum effects and heat dissipation issues. As a result, there has been a shift towards alternative architectures, such as 3D stacking and new materials like graphene, to sustain the pace of progress. Quantum dot displays. Semiconductor technology has significantly impacted display technology. Quantum dots, semiconductor nanocrystals, are employed in quantum dot displays, QLED, offering improved color accuracy and brightness in comparison to traditional LED displays. This innovation has enhanced the quality of visuals in televisions, monitors, and other display devices. Internet of Things, IoT. The rise of the Internet of Things, IoT, has been made possible by advances in semiconductor technology. Low power, small form factor chips enable the connection of everyday objects to the Internet, creating a network of smart devices that can communicate and share data. This has implications for home automation, industrial processes, and healthcare, among other fields. Artificial intelligence, AI, and machine learning, ML. Semiconductors play a crucial role in the development of AI and ML applications. Graphics processing units, GPUs, which are specialized semiconductor devices, are widely used for accelerating neural network computations. There is also a growing interest in specialized AI chips and neuromorphic computing, inspired by the structure and function of the human brain. Quantum computing advances. Researchers are actively exploring the development of quantum computers, which leverage the principles of quantum mechanics to perform computations that would be infeasible for classical computers. Quantum bits, or qubits, utilize the unique quantum states of particles, such as electrons, to represent information. Though still in the experimental stage, quantum computing holds the promise of solving complex problems in areas like cryptography and optimization. Semiconductor industry collaboration. Collaboration among semiconductor manufacturers, research institutions, and governments has become essential for addressing complex challenges and driving innovation. Consortia and collaborative initiatives aim to pool resources and expertise to tackle issues like semiconductor manufacturing processes, materials research, and workforce development. Environmental and sustainability considerations. As the demand for electronic devices continues to grow, there is an increasing focus on the environmental impact of semiconductor manufacturing. Efforts are being made to develop more sustainable practices, reduce energy consumption, and minimize the use of rare and environmentally sensitive materials in semiconductor production. Security and privacy concerns. With the widespread integration of semiconductors in critical infrastructure and everyday devices, there is a growing emphasis on addressing security and privacy concerns. Secure hardware and encryption technologies are being developed to protect sensitive data from cyber threats and unauthorized access. The story of semiconductors is dynamic, with ongoing research and innovation shaping the future of technology. From enabling powerful computing devices to driving advancements in AI, IoT, and quantum computing, semiconductors continue to be at the forefront of technological progress, influencing nearly every aspect of our modern lives. The story of semiconductors is ongoing, with researchers continually pushing the boundaries of what is possible. As we move forward, innovations in materials, architectures, and applications will likely shape the next chapters in the fascinating narrative of semiconductor technology. Thanks for watching. Request you to subscribe the channel.